Hello everyone. Are you able to see my screen?
Yes, sir.
Okay. Yeah.
Some lecture. Lecture online.
Hello Sai, can you mute yourself?
लिया था ना पेन मैंने रिटर्न किया मैंने ले लिया हाँ इससे फोन का okay I will forward to
Sai Pranav, please go on mute. Sai Pranav. Hello everyone. This is the first live interactive session for the course of the Artificial Intelligence and Machine Learning in the Material Science, which is being instructed by the Professor Krishanu Biswas. I'm the TA in this course, and my name is Shivam Aggarwal. I'm the PMRA fellow at the IIT Kanpur. So this course is this live interactive session will be mainly related to the what he taught in the first week, especially. So now let us start. In the beginning, so I started with the artificial intelligence. What is the artificial intelligence? Artificial Artificial intelligence or AI is the ability of the machine or any computer to make the human mind decision making and the problem solving capability. Like if you see the uh, any machine can't do anything without any assistance of the human. But if any machine can or computer mimic the human mind decision making or the problem solving capability, that will be called the artificial intelligence. Like human have the natural intelligence, but if we see if any machine get that intelligence, that will be called artificial intelligence. Then there is a term which is coined in the lectures, that is a machine learning. And what is the machine learning? Machine learning is basically is the subset of the artificial intelligence. What will the machine learning will do? Machine learning is like if you just like any machine, you get learned. Just suppose like any student is any student in the class, and I told that to the student like 2 plus 2 is equal to 4, and then I told him like 2 plus 1 is equal to 3, and in the next time I will told him that 1 plus 2 is equal to 3, and similar kind of operation I told him, and after a certain time we will see in his mind it is uh, by default told like giving the answer to any question like 2 plus 4 is equal to 6 by the training which we given him to the previously. So same is the machine learning. Machine learning is basically the study and the process which provides the system to learn automatically on its own through the experience had to improve the according to without being explicitly programmed. Like we have not given him any program like to yani ki there is a plus operation in the program or any operation. Just it use the previous data and give to the answer to the new data. Then there is another term in the lecture, that is the deep learning. What's the deep learning? Deep learning is basically the subset of the machine learning. It is not nothing new, but there is a difference between the deep learning and the machine learning. Having the it is a subset of that, but here machine learning in the deep learning, it is used generally on neural networks. Neural networks is a kind of a different thing. Uh, like here, it is mimic the behavior of the brain. Like our brain is work on the neuron based. Like we got information from the neuron and they processed that information and gives the output. But in similar way, if there is any any algorithm which work on the neural based, that is come in the deep learning part. How it is a different from the machine learning? Mainly deep learning algorithm focus on the information processing pattern mechanism to the possibly identify the pattern, just like our human brain does. Like our brain does process the information, same as deep learning also do the same. If you can see, this is the plot here. You can see deep learning is the part of the machine learning, it's a subset of the machine learning, and deep learning is based on the deep neural network. Like, and the machine learning is a subset of the AI, but machine learning is the ability to learn without being explicitly programmed. Like we are not you are not giving the computational detail to the model. You just giving the data and you give the input and the output, and it will process that data input and output and give the output if we give the any new data inputs. And what is the artificial intelligence? It is the engineering of making intelligent machine and the program. Like they can do the decision making just like us. So what is the characteristics of the AI, any AI system that will observe, and it should be have the analytical ability to perform, and it has the problem solving ability, and it should also learn from the its experience. Like just as a human, if we do something wrong, then we learn like this thing is a wrong, and from the next time we will do the correct things. Same as if any system do these things, that is will be artificial intelligence system. And there is two categories in the AI system. There is a narrow AI and the general AI. What is a narrow AI? Narrow AI is the like just a it is a artificial intelligence system, but for a specific reason. Like it will do the any specific task. Just like if you see the chat box in the your phone, WhatsApp Meta AI, and there's a chat GPT kind of thing that will answer your ad. You can just chat them. You can't like proceed anything. You can't told him like do any other work from that giving the answer. Same as like face detecting AI. Like you, there are the like different things there are with like in the airports, etc., which will see the face and detect what the detail of the person. And then there is a general AI. General AI is like it's a term for the like the any artificial system which can do anything. Like there is just a concept till now. Like as we human, we can't just do any specific work. We can do anything. Like I can solve math problem. I can give you the answer on the chat, and I can detect the faces. Similarly, to the human, if any AI do any work, then it will be the general AI. Application of the AI, you can see around us, there is a like a different use of the AI is used, like the speech recognition and the customer services. Like there is a some customer services which can answer using the AI systems, and the computer vision and the recommendation engines like you using your YouTube and Netflix, etc. Then if you see any content on this platform, they will recommended you thus likewise shows on that. Similarly, in the like for the music also, you can see the same. Like uh, if you listen any song, then it will recommended you the likewise songs. Like if you listening the sad song on the YouTube, it will shows the sad song in the row. And similar way, if you see the like any uh, thriller movie, then it will show the recommended you the thriller movie, and you will see that there is a recommendation of the all the thriller movies in your uh, feed on the YouTube or Netflix. Automated stock trading, like there are the many services there which can show the like prediction of the stocks, how they will work, and it will also now using in the health sectors also. Now, if we are, we will learn about the like what's the AI and the machine learning and the deep learning, but what's the need of the AI in the material science? Like if we see the materials, the humankind is the generation of the humankind is like we define the ages on the name of the like Stone Age, Iron Age, Bronze Age. Why? And there is if we see the some people call these ages like the silicon age. Why? Because nowadays like we are using the silicon more prominently, because there is a my computer, my mobile, my tablet, every digital device is making on the silicon. In similar way, like every age is have the different materials, and we need there is a need at every time of the new materials which is the more functional than the previous one. Like there is a, if you see there are the working people are working on the new semiconductor material which can replace the silicon in future. Similar way, people are working on the alloy system which we can replace the conventional steel and the different alloy system which are using till now. So there is always a need of the new material which is the more functional and the more efficient and the more green than the previous one. So like just an example, we will take how can we choose any design any material for a particular application. As in the lecture, sir give the example of the heat sink for the power electronics. Like if I want to choose any material that will be good for the power, for the heat sink application in the power electronics, that should be, there is some characteristics which we need. That should be have the maximum service temperature around the below the 200 degrees Celsius, and the it should be electrical insulator, and it should be the thermal conductor, because we want to dissipate the heat around that. So it should be have the highly thermal high thermal conductor, and it should not be heavy. Like it should be have the low density, because if that will be the heavy, our device will be heavier. And if we want to design, these are the constraints the my material should have. And there are some free variables, like I can choose a different material, and I will have the different processing for that to make that material. So how can I think about this material? If I see there is a constraint, it should be have the service temperature between below the 200 degrees Celsius. So first I will see the different kind of material and their maximum service temperature. If I see, it is a 200 Celsius. So if I can see, below the 200 degrees Celsius, there are the only metals and the polymers which have their service temperature below than 200 degrees Celsius. And if I see the ceramics and the composite, they have the maximum service temperature above that. So there should be for this application the only two kind of materials is left, metals and the polymers. So if I look for the different another properties for the metal and the polymers, there are the thermal conductivity and their electrical resistivity should be, if I see here, electrical, that should be the electrical insulator, yani ki, it means rho value should be below than the 10 power 20 micro ohm centimeter, and it should be the thermal conductor. So thermal conductivity should be greater than the 100 watt per meter Kelvin. So if I look here, there should be the two possible choices here, first one is the metal and second one is the polymers. So if I see for the polymers, they have the high electrical conductivity, but their thermal conductivity is low. But if I look for the metals here, the aluminium and the copper have the suitable values for this application. That's why so we can choose the aluminium alloy for this application for the heat sink. In similar way, if I want to design any other material, there are the only four constraints. But if there is any material which have the large constraints, it should be have more things, like here is only four constraints. So for that purpose, we have to look for the different parameters of the material. Generally, the human eyes cannot see. Like here is a two graph I can see, and I chose according to that. So if I want to look for the new material for this application, I have to work on the things which parameters decides these properties of this for this application. So now material discovery. So for every application, there should be the need to find the more functional material for that application. So I can see the finding the new material with the targeted properties. Like the target properties, it could be anything for the electronics, it should be electrical conductivity, band gap, or many things like mobility, etc. And for the structural thing, there should be like the mechanical properties, strength. So finding the new material with the targeted property is the tremendous importance of the technological development of the field, like the clean energy, national security, resilient infrastructure, and the human welfare. So there is always a need of the material discovery. But in the material discovery, there is a problem. If we discover the material by using the trial and approach method or any other method like the intuition based discovery and the instant Peter's discovery, there is a problem in that. If I use the trial and error approach, there should be the large number of the experiments I have to do, and that will be the costly and the time consuming as well. So there is a quite inefficient in for that purpose. So to accelerate the material discovery, there are the different approaches people are used previously. Here you can see the paradigm in the material science. First people just in the below than the 1600, people are used only like empirical science, like they have the data, and they used as empirically, like there should be the just see the relation in between that, like there is a property, if I say any property, A is the function of the different parameters. So they prepare a empirical formula for that. But after the 1600, there are the like the theoretical science that use the science, give the scientific laws for the like thermodynamics, quantum physics, and quantum chemistry, and there are the electromagnetic, electrodynamics, and many laws for the chemistry also. And that gives all theoretical knowledge about the design of the material. After that, third paradigm, after the 1950s, people are using the different approaches like DFT and the molecular dynamics, or many simulation, which are based on the these scientific laws, like the which were discovered before the 1950s, and use those laws, and program, making the program according to those laws, and predict the properties of the materials. And that plays a crucial in the designing the materials, like at the atomistic level, and they are the molecular level. But that is also the very time consuming and highly computationally heavy. So that will need the expertise in those theoretical science and as well as the computational science. But after that, after the 200, like in the 21st century, there is a big data driven science is uh, coming. Like here, people are using the database which were made earlier, or making at this time. They use those database and learn the machine learning models, or like making the any program which learn from that data and make the prediction for the new thing, for the new material, or the for the new inputs. So that will help into the accelerated accelerated discovery. Like here you can see, if you have any question like what is the property of that material, and how I can decide the properties of this kind of material. So then first we will see its properties and make an data set, and then we give to the machine learning that will hypothesize that, and after that we test that hypothesis, and then we will access those tests, and after that we will give the report. Yeah, it means we can make see the what is the hypothesis is correct or not, and making the changes according to that, and then we will give the answer. This loop can make the autonomous testing of the material, and help us to accelerate the discovery of the materials. So this is the thing. So we can get the big data from these paradigms, first, second, and the third, like by the computational science, by the theoretical science, and the empirical science, like the conventional trial and error methods. And we can get those data, and we can use that data in the machine learning or any AI technique, and we can get the prediction for the undiscoverable materials according to that. Uh, Now, how can AI help in the discovery of the materials? So, if we see the machine learning, these are like how the machine learning work. If you can see, like you have any data set, like I have a data set for the any family of the materials, like the material one have the property value one. Just for example, just take the band gap. Okay, I have the material one, that's the band gap value, and there is an n number of the materials that have the their corresponding band gap. Now the materials, I have the materials in the form of the chemical composition. like the chemical composition. But that any machine learning, any machine can't understand that chemical composition. So after that chemical, I have to convert that chemical composition into the fingerprint. What's the fingerprint? Like a fingerprint is the like the features that have that all the property, like all the signatures of that composition, chemical composition. Like I have the chemical composition like just any halide peroxide, ABX3. Like I have just taken the like strontium tightening, SRTI. SRTiO3. So I am looking for the band gap for this material. I have to convert this chemical composition into the its fingerprints. What's the fingerprint? Their fingerprints are is the signature of this composition that will that will define this composition explicitly. So I'm looking for the band gap value. So I will look for the like the what are the properties of the elemental properties of the strontium titanate that will decide the band gap. So according to that, I will convert this composition into the fingerprints. Like if I just told you for the strontium titanate, the band gap will be derived from the like the A site or B site and the X site of the material. It means titanium and the oxide and the strontium. So the different properties like the electron affinity, electronegativity, ionization energy, or there will be the any property that will be like I can get from the literature, which properties defines the band gap of this composition. I can take those as a fingerprint of this chemical composition, and after that I convert this data into the only fingerprints and the property value. So I left the chemical composition. What is the chemical composition? Because any machine learning model can't take that composition. So by that fingerprint and the property value will be the output of that composition, and the fingerprint is will become the input for that model, and that will train according to this. Like property value is the function of the this fingerprints, and it will make a like empirical formula in the model. Like it will making the any empirical formula or any the formula which like it cannot be explained. Sometimes any machine learning model can give the you the empirical formula like in the linear regression kind of models, the like simple models. But in the complex model, you can't get that formula, like that empirical formula, how it decides the value, property value for these inputs. And then we will try the prediction for the different F1, F2, and FIN, and check for the property value for the any material which is not given to this model. And after that, we will evaluate the model. Is it working fine or not? So if I want to use any machine learning model, so I have to divide any machine learning task into the 5 parts. Generally, it is not limited to the 5. Sometimes it will be the 4, but majorly it can be divided into 5 parts. Data preparation, like in which we prepare the data can be the like theoretical data and the experimental data. Sometimes we can got those data from the literature, and sometimes we have to make our own data set, like in lab synthesis or by using the computational techniques. And after that, we have to do the feature engineering. What's the feature engineering? Like in the previous slide, what I told the fingerprints, those are the mainly feature. What is the feature of the input data? And after that, we will use the model selection. Model selection is a complex task because we have to look for the which model can be used for the, that data set efficiently. So we have to do those things like deep learning would be the best for these, and there are the different kind of model which will be discussed in the next classes. And after that, we will evaluate the model. Like we will check the efficiency of those models, how they give the prediction. Like they are bad performing models, or they are good performing model. Then we will evaluate those. And after that, the prediction. After that, we give the prediction according to those valuation model. In the prediction part, sometimes we prepare on data set and give to the model, and it will give the prediction according to that. But sometimes, like what we told the AI, it will give to you the best performing material to itself. So for those purpose, there are the some models which can be used, like there is a generative uh, neural network which can give those things. So we will discuss those later. So now we will see the some examples, like the some case studies, how the machine learning can be used for these purposes. Like here we will not be discuss the things like how the things are working, but mainly we will see here what you can do in the future, or you can make on project according to that. So there is a first example, uh, band gap and the photovoltaic parameter prediction of the halide perovskite by using the ML. Okay, so for this in this work, like if we take a data set from the literature, like which have the this kind of data like MEPB, R3. It is a material like maybe who don't know about the halide perovskite, that have the chemical composition in the form of the ABX3, and it is a semiconducting material which is widely used in the photovoltaic application in the last decade. So it has the ABX3 structure, and you can see there are the in this data there is the MA. This MA is the organic molecule methyl ammonium. And this is the 4-memidinium Fa. So here you can see Ma, Pb, Br 0.3 or I 2.7. So for the X side there is a 2 elements, and here is also the 2 elements, and for the A side here is also the 2 molecular uh, organic molecule. So this is the kind of the data which we have used. This is the ABX3 composition, and I have the band gap for this composition, and the photovoltaic parameters like the open circuit voltage and the short circuit current and the efficiency of those solar cell, which are made by using these halide perovskite materials. So after having the data set, why we you working on this material? Like generally people are working on the lead based material, which is the like unstable in the moisture, light, and the high temperature. So we have to looking for the material which is like stable as well as the highly efficient. That's why we working on this. So after that, having that data, we have to convert into the features. So for the featureization, we look for the science of that material, like how the band gap is working for that material, because the band gap is the crucial parameter for the photovoltaic parameters also for any semiconductor. So first we will see how the band gap of the material defined in this case only. Okay? So for this, we look for the band gap of the halide perovskite is decided by the s orbital and the p orbital of the B site, because the lead at the B site here, and p orbital of the X site. So because you can see here the valence band is formed by the antibonding molecular orbital of the p orbital of the I and the s orbital of the lead, yani it means B site. And conduction band minima is formed by the antibonding molecular orbit of the uh, p orbital of the b side and the p orbital of the x side. So if I want to check the band gap of this material, I will look for the like the properties, elemental properties of the b side and the x side. So that's why we choose the properties of the x side and the b side to predict the band gap and the photovoltaic parameter. And for that purpose, we choose these properties like the ionization energy of the B site, second ionization energy of the B site, third ionization energy of the B site, and the electron affinity, electronegativity of the B site and the X site to predict the band gap and the other photovoltaic parameters. So in the previous, we have not only used this parameter, we use the different parameters also, like different features also. But at the last, we just constrained ourselves to these 8 features. Why? Because after you have done the featureization of the composition, you have to also look for the like some input feature as input feature are the correlated to itself also. As you can here see, the ionization energy 1 and the ionization energy 2b highly correlated to itself. So if I use here is a difference actually, but if you look other properties, they have the like their correlation factor is around 1. So they are linearly correlated to each other, one plus 1 or a minus 1, both can be. So they are highly correlated and give the same information to the model. So first we have to eliminate those same information giving features. For that purpose, we have to look for the correlation factor, and we check generally if the correlation factor is less than 0.95, we took those features as an input and left the other features. But there are the some other methods also. There are the like to reduce the feature size. So there are the like the PCA analysis, which also used to reduce the size of the featureization, which is an algorithm to eliminate the highly correlated features, and it will also make the new features which are not correlated to each other. And you can also give them the size of the features, like I just want the 5 features for the model, so I can give it to the number of the features I want. So it will prepare the like only the 5 features which have no correlation, like very low correlation to each other. One minute. Now, after the featureization, there would be the model selection. Like what's the model selection? Model selection is just like you have to choose uh, the ML models, which will you have to select the which model can be used for your data. Like there are the different kind of the ML models which we will not discuss here. Uh, like there are will be the different kind of the ML model, like the linear regression, support vector regression, support vector machine, random forest, gradient boost regressor, and the XGBR, XGBoost regressor. There are the lot of algo algorithm which can be used to train our model. Ah, just I forgot.
class.
What happened? അറിയത്തില്ല എവിടെ പോയെന്ന്. ആ മനുഷ്യനെ കാണുന്നില്ല. ഓ
वट्टे वट्टे
Is the meeting on or it's closed? Right,
ആർക്കറിയാം എന്തുവാന്ന് ഇതിനെ പോലും കാണാനില്ല.
புகை ஏற்றிட்டே இருக்கான். இப்பெல்லாம் இல்ல, இப்பெல்லாம் லைட் கலந்து லைட் போட்டாங்க. நாட்டு பக்கம் போனீங்கன்னா तुम कहोगे तो छोड़ दूंगा मैं से. तीन चार बार खिला चुकी है अपनी लाइफ में. जब तक लोग एक जेब से नहीं निकलवाते शांति है. अनिता दी से बात हुई थी तो बोल रही थी तबीयत ठीक नहीं है, मेरा मेडिसिन चेकअप कराने लाना था. वेट भी बढ़ रहा है और वो लीवर में प्रॉब्लम है. उनके पास तो बहुत सारी चीजें रहती है ना, और पता नहीं कौन है वो तो हो गया का नाती 12 साल का बच्चा स्कूल में चलते था और स्कूल से आते ही बोला कि मुझे पानी पिला दो नहीं तो मैं मरने वाला हूँ. जब तक डॉक्टर आता तो आया फिर डॉक्टर से उसने कहा तो मुझे तो ऐसे ही देख रहे हो, मैं तो लगने वाला हूँ। क्या था वो लड़का?
आई थिंक हम सबको लेफ्ट हो जाना चाहिए, कोई आ नहीं रहा।
அது கூட நாளைக்கு எடுத்து அங்கே அப்டேட் பண்ணி எடுத்துருவாங்க. அது புரியுதா அங்க
Hello everyone. Sorry, I just lost my internet connection lost. Hello Ravi, can you mute yourself? Okay, uh, let's start from here. Okay, uh, here we are. I'm giving the example of the machine learning model, how the machine learning models work, and I'm using the example what work we have done. Uh, so this is the halide perovskite. Halide perovskite. There is a work on the band gap and the photovoltaic parameter, the prediction of the halide perovskite. What is the halide perovskite? Halide perovskite is a kind of material which have the chemical structure of the ABX3. Okay, which is written here. It has a chemical structure of the ABX3, where A is a monovalent, and B is a divalent, and X is a halogen anion. And it has the cubic structure or the orthogonal or etc. And these material get a lot of attention in the last decade due to its astonishing the optoelectronic properties. Like it is widely used for the solar cell application, and is my video is visible to everyone? Okay.
Your slide is visible, sir.
Okay. Okay. So it is a outstanding optoelectronic material which is widely studied in the last decade. It has the tunable band gap and the high charge carrier, high absorption coefficient, etc., which make it the suitable material for the solar cell application. But these materials have the problem, it is quite unstable in the ambient condition like moisture, light, high temperature, and the electric field also. So the which make the imperfect for the commercialization to this material. So the people are working on the finding the to discover the new material, new halide perovskite material which is stable as well as the highly efficient. So we are working on this material, and in this work we choose the few composition which are studied in the literature experimentally, and we compile all the data from the literature with the band gap and the photovoltaic parameters of that composition. Like VOC is the open circuit voltage, and the GSC is the short circuit current density, and the PC is the photo conversion efficiency. It means the mainly efficiency of the solar cell, how much energy it will convert, solar energy it will convert into the uh, electrical energy. So after that, I will discuss about the featureization. Like for the any machine learning work, featureization is most important part, because in especially in the material science, because in the material science you have the chemical composition, and you can see if you don't know about this chemical composition, like many of you don't know about this material, maybe I think you don't know how it will be correlated to the band gap, and how it will correlated to the short circuit current or open circuit voltage, or will be the how it will be correlated with the conversion efficiency of this device. So for that purpose, we have to convert this chemical composition into those signature or on those fingerprints, so any machine learning model or machine can understand those. So for that purpose, the featureization is mainly done. But featureization is a crucial part. It depends on your system to system, which system you are using. So for that purpose, you have to look for that. So I'm working on the halide perovskite. So we saw the I want to predict the band gap and the photovoltaic parameter. So I will look for which parameters of this chemical composition decides the band gap. So for that I look for the literature, and I found that the band gap of the halide perovskite or any perovskite is largely depend on the B site and the X site of the material. And here you can see this is the molecular orbital diagram here. Like you can see the p orbital of the B site and the I orbital of the p orbital of the X sites. Uh, Antibonding between them make the valence band maxima. And here you can see the p. Sorry, I just say wrong. The s orbital antibonding between the s orbital and the p orbital of the x side makes the antibonding, makes the valence band maxima, and the conduction band minima is formed by the p orbital of the b side and the p orbital of the x side. And so I can choose the features according to that. Take in this molecular orbital diagram into my mind. So the p side, b side and the x side play the crucial role to decide the band gap of the material. Besides that, there are the other factors also. I can't avoid those, like the a side also, because the size of the a side also plays the crucial role. But we look the different aspect for that. So I'm not discussing those things. So I choose the different electronic parameters which decides the p orbital and the s orbital and the p orbital of the x side. For that purpose, I choose the ionization energy of the b sides, first, second, and the third, and the ionization energy of the x side, electron affinity of the both the sides, and the both side elements, and the electronegativity of the x side. There is a factor like you can see there are the number of the a side and the b side element. If you can see, there is here is the two element at the b side. Here is two elements at the a side. Here you can see the two element at the b side. So for that purpose, we took the average of these properties for that particular sites. Okay, that approach we call the PAEP, like the positional average uh, elemental property. PAEP. Positional average elemental property. Like for the different site, we use the average of the element which are occupied that site. Like in this side, Me and the Fa occupied at the A side. Here B, bromine and the iodine occupied the X side. So we take the average of that average property of for that site. Okay. And after that, I have discussed about the which feature we will use. Actually, I have take the the background of the material, how the band gap of correlated with the input features. Then I have also look I use the 8 properties, but in the beginning I have not choose only the 8. I choose the large amount of the properties, and I found that that here there is a Pearson correlation coefficient which decide input properties and the output properties are correlated to each other or not. If you see the band gap, for the band gap, ionization energy B has some green well green color, so you can see this color is belongs to here, like it will be like the correlation between the 0.25 and the 0.5. So in similar way, you can see the how the input properties is correlated to the output properties, or they are correlated or not. Sometimes it will be like these properties are not correlated, so you can avoid them because it is not giving you any input. And besides that, here you can see the correlation between the input properties and input properties. So if you have any properties which have the correlation factor larger than the 0.95, both of those input properties give the same information. So for that purpose, what we have done, we drop those properties generally. Or there are the other methods also. You can see the Pearson correlation fact coefficient table and eliminate those features. Or besides that, there is a some algorithm like PCA and many things which can eliminate those features which are highly correlated and make the new feature also, which are not correlated to each other. And generally, the correlation factor between the input feature should be below than 0.95. Generally, people are used, but you can take it should be lower than the 0.9, 0.8 according to your one. After the featureization, you have done the featureization of your data set, it means you have converted your chemical composition into the some numerical values. After that, that's the data you have to convert it into a 2 part, or sometimes it is converted into the 3 parts. First part would be the train set, then the test set, and train and test. Why? Because if you are training any model by using your data set, so you have to evaluate those now. For the evaluation, you have used your test data set, which is not using in the training of the model, and you train your model by using the train data set. And if you want to evaluate those model, then you will give the values of the test data set, and you will get the prediction for those by using the trained model. And you can compare the predicted value between the actual value for the test data set and the predicted value, and you will evaluate according to that. So after the data set, splitting the data set, you can choose the different ML model. Like here we are working on the linear regression, random forest, support vector machine. There are lots of algorithm which can be used as a ML model. Okay, so we are not discussing those algorithm how they are working, but here you can see those algorithm are used to train the model. Train the data set, mainly input properties and the output properties. As your input properties is trained by using the trained data set, then you evaluate for those the test. Here you can see we have evaluated for the test also as well as the test data set. And here is the R2 score for those. For the test data set, we have not gone for the train because the ML model is trained on that data set. That will be the good answer. And here you can see if any material have the band gap around the 1.6 in the test actual value, it is the predicted value is close to the 1.6. This is a very low error in this. So that's why it in similar way this line also shows this is a clause. This plot is called the parity plot. Here you can see the all the data point is in between the this straight line in the between. So you can say your error is low if these data points are scattered around this here in such a manner. So that is there is some large error into the model. So you can try to minimize that, or sometimes it is the best which we can get. After the training the model, then we will evaluate those model. They generally for the regression model, like where we predict the numerical value. For those purpose, generally people are use the evaluation matrices like R2 score, uh, root mean square error, and mean absolute error, and Pearson correlation value, yeah, R value. These values are used to validate the model. In my work, you can see for the band gap random forest performed well with for the maximum R2 value 0.96, and the RMSE should be lower, should be minimized for the best performing model. So here I got like the 0.051 and the 0.038 mean absolute value and mean absolute error, and the R value is around 0.98. And here you can see for the every prediction output we got this score, and which is quite good for our work. And after got this model evaluation, we have to predict we have to use those model to for the prediction. For the prediction part, there are the two types of work we can do. First, we will prepare our own data set. Like I have prepared like I choose the 10 cations for the A site, and the 11 cations for the B site, and the 4 and 9 for the X site. Like for the A site, I choose like uh, methyl ammonium, formamidinium, uh, vanadium, cesium, rubidium, and many more. Sorry. Uh, Methyl ammonium, formamidinium, rubidium, cesium, and ethyl ammonium, and many more. And for the B site, I have used lead, uh, tin, strontium, barium, etc. And for the X side, this is the halogen anion. So this is our Ar, chlorine, and chlorine. And I use in the ratio of the 0.25, like it's a multiple of the 0.25, 0.25, 0.25 for the A side, B side, and the X side. And I make a large data set of which have the like 25 million composition. Then in the halide perovskite, in the perovskite, there is a factor like the tolerance factor and the octahedral factor, which decides its formability, like perovskite structure would be formed or not. For that purpose, we constrain the tolerance factor and the octahedral factor for this composition should be in this value. Like tolerance factor would be uh, between in the 0.8 to the 1.1, and for octahedral factor should be like 0.4 to the 0.78 for this one. And after that, we predict the band gap for this material, and we know for the ideal for the solar cell ideal band gap is around the 1.3 by the around the Shockley-Queisser limit. And so we constrained the prediction band gap around the 1 point electron volt to the 1 point electron volt, and we removed further composition. And these selected composition are around 0.7 million, and this composition have predicted this PCE value by our best model for the efficiency for the perovskite solar cells. This is the work how you can use the machine learning to predict the band gap. Now you can told me like I don't 0.7 millions composition will be good for node, but if you see here you can get the 25 million composition, and after this tolerance factor you can shortlist only the 18 million, but after prediction of the band gap, and you will get the only 0.7, which will be uh, have the uh, have the reasonable value for the perovskite solar cell application. Uh, There is another thing for you can do for the prediction. Most of the people are working like here we have not giving these these prediction value to the model. You can give like I have this A side, B side, and the X side, and your ML model will use properties of the A side, B side, and the X side, and try to get the maximum value for the PCE on itself. Like in this work, I have to look for which composition give the highest PC value, and your ML model can do that also. So people are working on those things also. That model is generally generative based generative adversarial neural network GAN, which is widely called the GAN. So there is another work. It's a I have the talk about the like the how you can predict the numerical value, and in this work you can use here people are using the image how to predict that. As you know, in the material science, you know there are the sorry there are the different microstructures in the steel, and people spend lots of time in the microstructure uh, to divide to analyze them. So for that work, Nikhil Chorase et al. Prepare a ML model which can give what is that microstructure. For that purpose, they prepare they make the on data set by using the computational plus experimental both, and they combined these two approaches to make their own data set. For that purpose, they prepare a this kind of microstructure, and they use the experimentally collected images of the ferrite and the pearlites, and they use these images on the site of this particular microstructure and make their own microstructure. It is the artificial microstructure which they prepared, and this prepared microstructure they used as a input set input, and they after using this input they prepared they used any UNet ML algorithm. Don't bother for this what is a UNet, and after that they after the model preparation they try to get the like the evaluation of those models, and they got the high accuracy around 0.995 for this model, and this is the R value which is around 0.9945 for the unit, and this is the some uh, some micrograph they use to get the model prediction and the ground truth. What is the you can see this is the microstructure, this is the pearlite structure actually, but our model give this, and you can see these both two are the close to each other, so it's giving the working the good. Here you can this is the artificial microstructure, here is the real microstructure, and you here also you can see it is working good here also with the experimental micrograph also. This is the also some micrograph they use to that, and they got the high accuracy here also, and this work use the imaging processing here you can ask me like what featureization they have used like because I in the previous work we have used the featureization as a main thing, but for the featureization there are the some algorithm which also accommodate the featureization for the images also. Like for the images you can't give any numerical value by your own. If you want to give the any numerical value for this image, how you can give that? So for that purpose, your ML algorithm can deal with that. And it is a like you can see here is a ideal fitting, and we got a very good result, and it is able to it is able to uh, give the differentiate between the pearlite and the ferrite microstructure in steel microstructure. After that, I can show you also the one example. This is from the work of the Rahul Mitra. In this work, they have used data from the literature also, and they calculate the features as the previous work have done in the halide perovskite, and then they use the different models and compare those models. And hyperparameter tuning is a thing which we done in the ML models. When you will discuss about the ML model, we will discuss about the hyperparameter tuning also. Then they compare the accuracy of the material models, and then they will finally select the final model and give the prediction according to that model. And this is the input data set of him, and here is some table, some composition which he have used for these high entropy borides. You can see for the group from the group 2, they use the barium, magnesium, calcium, strontium, barium, and for group 3 to 12, they got the stadium, titanium, vanadium, and the group 3, they got the they use the lanthanum in the data set. And there you can see the quaternary diborides and the quaternary diborides, which he have used as a input data set. And in this, he classify the data set into the a single phase or the multi-phase. For the featureization part, he have used the ratio of the radius of anion and the radius of the cation, and he also used the Pauling difference between the Pauling electronegativity and the Mulliken electronegativity and the lattice mismatch or the enthalpy of the mixing, entropy of the mixing for as a input features. And he used the Pearson correlation matrix to see how these features are correlated. You can see the correlation between all the feature is below than the 0.95. So there is a no, there is a have a good correlation factor. So here you can see for the input there, because the input correlation should be lower than the 0.9 approximately. And this is the accuracy for the different model which he got. And it's a, you can see the random forest give the good accuracy for the training set. But if you see for the accuracy for the training set, it is not a good. But if you see the KNN for the training and test, it is showing the good accuracy. So what KNN model is the good, and they choose the final model as a KNN. And here is the accuracy plot for those. And after that, this KNN model is used for the prediction for the quaternary and ternary diborides. So here you can see I have given you the 3 examples how the machine learning used for in the material science to predict the band gap, to predict the numerical value, to classify the their multi-phase or single phase, or you can also use the image processing to get it is the pearlite structure or the martensite structure or the any other structure. So this is the how machine learning can be used in the material science. So I'm going to end this lecture. If you have any query, please ask in the chat box. Is there any query? Amrit, what you want to ask in the phase transformation for the? So in the phase transformation for the still the validation error is more than the training. Okay, so I have to look for that. Validation error always larger than the in the training, because you use the training data set for the training the model now. So your model learn the training set. So the error for those model would be larger, low, below than the test data set. In exam, what type of the question will be asked? I don't know about that. You have to ask to the sir about this. Any other question? Maybe Amrit, you got my answer now, I think. So, but a model to be robust does not need to be less. So, you are right, but it should be the comparable. It is not be like that. You have the error about the loss. Just for example, uh, Amrit, I'm giving the answer to the Amrit. As you know, the loss between the in training set and the testing set is depend on the how your the margin. If you see in the this parity plot, you will get that this is very close to the this straight line at a 45-degree. So if you get the training testing set is far more than this straight line, then you can say this is not a robust. But you are getting the comparable values. You're not too much loss. So we can that's why we don't also look for the one loss. We also look for the 3-4 kind of evaluation matrices for this. Maybe you got my answer, I think. Any other question? Okay, let's end this session. Will you be providing any sample data set? I'm not sure about that. Maybe in the future you will get, or otherwise there are the very many data sets which are the openly access. You can got those data sets. I can in the next lecture I will show the different websites where from where you get the material science data set. Uh, now I don't know about the name of any website. I will. I know, but surely I say I will give you in the next class. Surely. Any other question? Sir, please can you share the PPT? I don't know you will be get these PPTs or not till now, but if I can I'm have the permission to share, I will share that. Any other question? Okay, thank you so much. I'm going to end this session. Sir, how can I increase the accuracy of a model? Of any model, you have to first decide which model can be used for your data set. According to that, you have to choose your model. If after that, if you choose your model, this model should be work best for this type of data set, you have to look for the hyper parameters tuning. What's the hyper parameter tuning? in brief, I can say you the hyperparameter tuning is the parameters of the ML model, any ML model. We can tune those to increase the accuracy of any model. Okay. Maybe Anthony, you got your answer. Any other question? So for the composition data from the literature with the Latin, maybe Riazul, you are asking for the like uh, uh, image processing work, I think. Are you asking for that work? Latin hyperparameter tuning. If you are confused in this term, you can go for this work. I will share it to you. You can go for this work and here you get this. No, sir, it is regarding the composition prediction for the algorithm. If this is for that, I don't know. I will look for this. What you told me? Hypercube sampling. Okay. In the next class, I will discuss this. Actually, now I don't know about this. Latin hypercube. Any other question? Okay. Okay, Riazul, I will look for this paper. Then I will tell you what is this. Any other question? Anyone else? Okay, everyone. Let's meet in on the Saturday in the next live interaction class. Thank you so much.